Thank you very much. My name is Qihong, and I am a third-year PhD student under the supervision of Professor Andrea Ianniro and Professor Stefano Dicetti. In the next 10 minutes, I'm going to try to fit a summary of my thesis. And to start with, let me say that turbulence is everywhere. And we cannot only find them in canonical flows such as turbulent boundary layers, wake flows, or shear layers, but we can also find them in many, many situations around our daily lives. For instance, in wind turbines, cardiac flows, weather, the cups of coffee. And just to give you a quick example, even today, we just heard the word turbulence many, many times. The good thing is that we know that turbulent flows are analytically described by the Navier-Stokes equations, and if we want to control them, we need dynamical models. On the downside, one of the main issues or problems is that the Navier-Stokes equations do not have a direct analytical solution. Usually, this type of flows are characterized by very nonlinear dynamics. They are very high dimensional, and as Luca was mentioning before, when we want to do experimental measurements, we also have some technological limitations. And last but not least, these type of flows are also characterized by a multi-scale character. Regarding the dynamical models, we have different types. First of all, we have white box models, which basically consist of solving the Navier-Stokes equations. Then we have black box models, which have gained a lot of popularity during the last decades. And basically, they are machine learning models which learn an input-output relationship between the data that you use to train the models. And finally, we have gray box models, which take the best of both worlds. And in particular, they're interesting because they allow us to obtain reduced order models, but with physical insight inside. The first ones, white box models, I'm going to leave them for CFD people. I'm going to focus only on data-driven models. And my interest is in this one because the models we are going to obtain, at least in my thesis, are going to be based on experimental measurements. In particular, my thesis will focus only on gray box models, taking this advantage of having the knowledge of the physics inside the model. Regarding the high dimensionality issue I was mentioning at the beginning, one of the main objectives we have is achieve a dimensionality reduction. This is because if we want to control the flow, we need interpretable models, and to do so, usually we want a complete description of the flow dynamics. We can obtain this either by simulations or experimental measurements, but in most of these cases, we have the problem of high dimensionality. Just to throw some numbers, in the best of the cases, in the 2D planar measurements, we are of the order of tens of thousands of degrees of freedom, which is still a large number. So here's where my thesis comes into play, which objective is to obtain data-driven models of turbulent flows and reactive flow control. But during these first years, I focused mainly on obtaining reduced order data-driven models. The first work I did was focused on surpassing the limitations from technology. In particular, let me pose you the following question. So I show you here a video of a man running. And the question I pose you is, if I stop it in a frame, can we estimate or predict what is it going to happen afterwards? So can we somehow know the dynamics from a fixed image? The answer is yes, because in our case, we are trained from the experiences we learned through our lives. We know how physics work. And also, if we look at the position of this guy, he's leaning forward, he's raising one leg, standing on the tip of the left foot, we can predict that in the next step, he's going to step forward. We can do something similar with turbulent flows, but in this case, the knowledge of the physics is going to be given by the Navier-Stokes equations. So this was the objective of my first work, where I wanted to recover the flow dynamics from non-time resolved flow measurements. So I did this work where I created a model which receives as input some full flow field measurements. I do the decomposition into modes. I obtained the simple reduced order models, and finally, I recovered the dynamics. In particular, the inputs were non-time resolved PIV measurements that, for those who are not familiar, PIV measurements give us velocity measurements, so velocity flow measurements. Then we decompose it into modes through proper orthogonal decomposition, which basically allow us to extract some bases from the data we are obtaining. So the idea is that these bases capture the dominant spatial and temporal features of the flow. Then we obtain the reduced order model by projecting the Navier-Stokes equations into the bases we obtained before. And here I want to remark that the knowledge of the physics is in this box. And finally, we reconstruct the time-resolved measurements. So all in all, in this work, what I did was recover the temporal resolution of some flow field measurements from non-time resolved snapshots. And this work has been already published in the Physical Review Fluids with open code and open datasets. Now, the next problem I wanted to tackle was the problem of multi-scale flows. So let me give you this example of the jet flow. We are seeing the velocity fields, but I want you to focus on the vorticity fields. And the problem here lies on the fact that in a same field, in a same flow field, we have different scales of different characteristic length with different characteristic times evolving at the same time. So the issue comes when we want to obtain a reduced order model, because if we want to capture the dominant features of each of these structures, we're going to need still very high dimensional models. So the next work I did was targeting this problem, and the solution was focused on doing a local dynamical analysis. The main idea behind this lied on the idea of dividing and conquering, where here conquer means doing a reduced order modeling of each of these parts. The key idea here is that we are not randomly dividing the space. We want to obtain different subdomains that are dynamically coherent. So they share the same dynamics into these regions. To do so, we created a reduced space that we call space manifold here, that we obtained from isometric mapping. And it works in such a way that if we have points in the flow that have similar kinematics, they are going to be closed in this reduced space. Then by applying a clustering algorithm, we obtain the following partitioning of the space where we have subdomains that share dynamics locally. After we have this partitioning, we proceed with the part of analyzing the dynamics in each of these regions. The advantage of this is that we're going to obtain local models that are more simplified and are more interpretable. This work is still under review. We have, it's divided into two articles. One of them is under review, and then the second part will be published, I think, within a month. Now, to recap, during the first 3 years of my PhD, in the first work, I did a Galerkin model targeting a time supersampling of non-time resolved PIV measurements, which has been already published with open code and open datasets. Then we wanted to tackle the problem of multi-scale flows. To do so, we created this divide and conquer complex flows work, where the idea was to tackling the problem locally and obtaining more simplified and local models. And for the incoming year, the I forgot to mention that this work is a collaboration with Guy, which is a postdoctoral fellowship in our group. Now, in what remains of this year, the next step is to do an estimation from sensors. Why? Because if we want to apply these models in real-time applications, we are limited by observability. We cannot put sensors everywhere in the flow. I mean, I wish, but usually we are limited in some locations. And also, if we rely only on estimations from a single model, in my case, the Galerkin model, for instance, after a certain time, the model is going to diverge from the reality. So here the objective is to use some probe measurements to steer and correct the estimations of the model. And finally, in this autumn, I will do my research stay at TU Delft under the supervision of Professor Fulvio Scarano, where roughly the main objective would be applying the models I developed during the first years into an experimental measurement with flow control. These are some of the main contributions I have done this year. The first article I mentioned, the second one is still under review, some conferences and courses and disseminations activities. And here I want to spend just a couple of seconds because disseminations and activities is one of my favorite. So I show you here a very short recap with a lot of faces that you might know. Yeah, that was all from my side. And if you have any question, feel free to ask me.